in multilayer fields, which we can also call thin film pockets. First thing that we should understand is about multilayers. Some of you may be aware, but for those who are not aware of what multilayer coatings are, let's see, this is a typical multilayer scenario. Here we have a substrate, then on top of that substrate we have films coated. All these, you see this red and blue regions, they are supposed to be layers of material, dielectric material coated on substrate. You see here we have interfaces. There is an interface between the blue region and the red region. Over here, see this is an interface. Then that continues, and there is another interface between the final or first coating and substrate. Okay, when light falls on one of these multilayers, it first encounters the air. Supposedly it is coming from air, the light is coming from air or vacuum. Then it encounters an interface here, and when it encounters a refractive index change, part of it will be transmitted and part of it will be reflected. You know that. And then on each of these interfaces there will be some reflections, and a fraction of it will be transmitted. And then the final output will be here. It is the E transmitted. Suppose we have E0 that is coming in from outside. What we are trying to do is to relate E0 and E. How much will be transmitted, how much will be reflected. Okay, there will be some reflections. Let's call it E0 prime. Then E0 prime divided by E0 will be, we will define it something like the reflectivity or reflection coefficient, that is, let's say R, and then Et over E0 will be the transmission coefficient, that is, let's call it a small t. These are some of the things that we can actually measure, or rather we can measure the square of that. That is, what we measure is the intensity, and therefore the square of it will give you the ratio between the intensities. And similarly, we will have to measure something like this. I'll call it capital T. You can relate all these things. There will be a refractive index N0 for this one, Nt for this one, and maybe let's say what if there's one coating N1, N2, etc. For if there are n coatings, then these will be the refractive indices. These are the things that we know, and we want to try and see what happens if an electromagnetic wave encounters a multilayer. The reflection will be from each interface. There will be some reflections, and these reflections will interfere because there is a definite phase relationship between them, and all these reflections may interfere either constructively or destructively. And what we will see interestingly is that we can tailor the refractive indices n1, n2, etc. And also, okay, basically since we have two types of, only two types of coatings here, there will be n1 and n2. And we can tailor the thickness, we can tailor, thereby adjusting the phase of the reflected beam. Uh, and make a device in such a way that it can sometimes transmit all the light, or more than 99% of the light that's coming in from here, or we can make it in such a way that all the light is reflected, nothing is transmitted. When I say nothing, it is only negligible amount is transmitted. And in one case we will call it's an anti-reflection coating because all the light is transmitted, and in the second case it's a mirror or high reflectance mirror. These are the two things we will have to work out from the theory that we are going to develop in this course, in this class. And then there is also something called interference filter. That is a special type of high reflectance combination, interference filter. That is to transmit only a very narrow band of radiation. It will reflect everything else except a small band of radiation. We know such a device, that's a fabry-ethylene, will transmit only a very narrow band. And we'll see that we can make out of these multi-layer films, we can make a fabry-ethylene, and then thereby making it a narrow interference filter. Okay, then one of the things that you know already is that there are certain boundary conditions. When a light wave or an electromagnetic wave encounters an interface, there are certain conditions that is derived from Maxwell's equations that the electric and magnetic fields of the wave has to satisfy. We call it boundary conditions. It basically says that the tangential component of the electric and magnetic fields must be continuous at the boundary. And now our aim is to compute reflected or transmitted wave amplitudes, and thereby finding out the reflectivity or reflectance of the surface. We will start with the simplest possible case where we only have a single dielectric field. Then you can adapt it to many layers. Okay, this is your situation. Here I have shown one dielectric film, single layer dielectric film, which has a thickness of L. Then it is coated on a substrate which has a refractive index of Nt. But by this curly curve here, I mean that this is infinitely long. It's very long. We don't consider any reflectance here. We don't consider that. We consider only reflections from this surface and this surface. Now, the material, the dielectric material has a refractive index of N1, and the light wave comes from a medium of refractive index N0. For the time being, we don't consider it as air. It's a medium. It can be water, it can be a liquid, it can be anything else. Even air is not absolutely one. Therefore, we formulate a general theory with n0 as the refractive index of the medium from where the light ray comes in. Okay, this is case of normal incidence. That makes things easier to apply the boundary conditions. And let's say K0 E represents vector K0 represents the wave vector of the incident wave, and E0, which is perpendicular to K0, represents the electric field of the incident wave. Then it encounters this interface here, and it's reflected. The amplitude is represented by prime, and again K0 is represented by K0 prime. It is a wave that is traveling in the opposite direction. Okay, if it is reflected not from this surface here, but this point there, it's reflected from here. But for clarity, I've used a separate line. Now, the total electric field in this medium is E0 plus E0 prime. We can take it that way because of normal incidence. Then it goes to the dielectric, where the K vector is K1, the electric field amplitude is E1, and reflected amplitude is E1 prime. Then the transmitted, the reflected wave vector is K1 prime. Part of it will be transmitted, and with the K vector KT in the transmission medium or in the substrate, it is ET is the electric field amplitude of the transmitter. We have two interfaces, one and interface 1 and interface 2. Oh. Okay, that's your problem. We straight away consider the boundary conditions. On the first medium, it is E0 plus E0 prime equal to E1 plus E1 prime at the interface 1, and also for the magnetic field H0 minus H0 prime equals H1 minus H1 prime, and that is equivalent to this one, that you can actually do. You see from Faraday's law, del cross E equals minus dou B over dou T. Here, if you consider a non-magnetic material for all the medium, all these three regions are non-magnetic. You can get to this equation very easily. Now, in order to get to the second interface here, the light has to travel a length of L, and it will add to its phase. Then the boundary conditions becomes E1 E2 for IKL, and E1 prime will become E1 prime E2 for minus IKL, where the direction has changed. Then that will be equal to the electric field in the third medium or in the substrate. Similarly for the magnetic field, and that becomes this equation here. Now we have four equations: equation 1, 2, 3, and 4. Now we have to solve it. 4 for what? We have to get these equations in terms of E0, then E0 prime, that is the reflected phase. Then in terms of ET, as I have discussed just now, It is easy. I mean, it's a bit of algebra. I have written it in the note that I have uploaded. Uh, See, we can uh, solve 3 and 4 for E1 and E1. You can do anyway. You can use any method. This is the one I use. Solve 3 and 4 for E1 and E1 prime and substitute them back into 1 and 2. You can maybe you can do it in the other way. From equation 3, that is this equation, uh, you can see E1 e to the power ikl is et minus this thing, and substituting this in equation 4, that's the second or the fourth boundary condition. Then we'll get, it's a direct substitution. You substitute for E1 e to the power ik here. Substitute for this one and substitute for this one. You get to this one, and just a few rearrangements. You get an expression for E1 prime. E1 prime is n1 minus nt divided by 2n1 et e to the power. You have to do it yourself or just refer to my notes. Now, substitute the value of E1 prime in equation 5. That is this equation here. You will get an expression for E1. Then we have expressions for E1 and E1 prime. What you have to do is to then do it for substitute it into equations 1 and 2. Okay, this is equation 1, is simple equation E0 plus E0 prime plus E1 plus E1 prime. We have expressions for E1 and E1 prime. You can eliminate, because that's some of the things that you can't measure. What is inside that medium, which is normally you cannot measure E1 and E1 prime. So that even if you get an expression which involves these two, it won't be very useful. That's why we try to eliminate that. Now it is E0 plus E0 prime is this one, and okay, just expand terms. Then you can club together e to the power ikl and e to the power minus ikl and e to the power ikl, and similarly these two. Then you get two terms with cos and sine, I sine, and this is what you get. Or if you simply rearrange it, because this is E0 prime over E0 is R, and this is T, and you can write it in terms of R and T, that's why just use this form to do it. Similarly, from substitute the same way in equation 2, if you substitute for E1 and E1 prime, you will get an expression like this one. Again, this is R, this is T. Okay, now you have two expressions, 8 and 9. We are coming closer to the final solution. This is okay. Now you have two equations. You can make it a matrix in the matrix form. This is by simply looking at the two equations you can write. This will be, the first equation will be 1 plus E0 over E0 over, okay, 1 times E0 over E prime is equal to cos KL minus nt over n1 sin KL times Et by Ez. And similarly for the second equation is so. Now, okay, you got a matrix equation. Just as I said, we substitute for R and T, and now we are going to use some of our techniques that we have learned. This is you define M as a transfer matrix. Here, one thing which I haven't told you is that at some point we have replaced K1 with K, because there's no point in keeping the 1 here, and that's why we have used K as the wave number for the dielectric medium or the film that we use. This is 2 pi over lambda, or in terms of vacuum wavelength, you can 2 pi over lambda 0 times n1. Now, okay, this is your, okay, if I written it here, this is 2 pi by lambda. Now, n1 is the refractive index of the dielectric layer. That we can, something that you can measure. Now, this matrix here is the transfer matrix for a single layer. Okay, now we have a much neat equation: 1 by n0, 1 over matrix 1 n0 plus 1 minus n0 times r will give you a transfer matrix times 1 of 1 nt times t. Suppose you have n layers, we know what to do. Of refractive index n1, n2, n3, etc., nn, and thickness l1, l2, l3, etc., ln. Here the refractive index comes through K, and L you can already see that. Now if you have n of these layers, we have to simply multiply the transfer matrices. We learned that relation between reflection and transmission coefficient in that case becomes M1 for first layer, M2 for second layer, product of all these matrices. That will end up with the final M, which is 2 by 2 matrix. We call the terms or the ABCD matrix. We call it ABCD matrix. Okay, this is equation, I have put that as equation 13. R and T in terms of ND. Therefore, okay, take R from here outside, R to inside, T inside, and therefore if you do this and solve for R, you will get straight away get this this expression here. Okay. At n0, b nt n0 minus c minus b nt n0 b nt n0. All these terms are the same, except the sign changed to plus in the denominator, which means denominator is always higher, R is going to be always less than 1. And for T, it will be like this, 2n0 divided by with the same denominator. And you can see the notes for derivation, because it's going to be a long derivation, and since you have the notes, you don't have to. I don't have to derive it, and it's not a very tricky thing to do. It's a straight algebra. Then reflectance and transmittance are given by these two expressions, as we have discussed. And this is something that we can measure. That's why we always use R. You cannot directly measure the electric field E0 and ET for E0 and E0 prime, the reflected amplitude. This is not something that you measure with a device. What we measure is the intensity, input intensity, transmitted intensity, and also the reflected intensity. That's why reflectance is important and transmittance is important. Okay, with that we stop with the theory of multilayer films. The notes are much longer because of the derivations, but this is uh, what it is. It is simply you consider the boundary conditions, and from that you eliminate electric fields inside the medium, inside the dielectric, and also once you have done it for a single layer, you try to do it, generalize it for multiples. Okay, thank you very much.